Okay, so what I'm going to think about today is demonstrating nuclear fission using a tub of Play-Doh. So initially thinking you're going to have your nucleus of your uranium-235 and a slow-moving neutron. And what's quite nice about this model is getting the idea that it is absorbed into the nuclei before it becomes unstable and breaks or splits. One of the big misconceptions that the students have is that they think that it hits it and then it breaks in half. So the idea that it's absorbed is really key. So then it gets absorbed into the nuclei, and then at which point it then becomes unstable and then breaks into two new smaller nuclei or new elements. As one of the key points is thinking a lot of the time they can confuse this with biology, because obviously at the same time as this they're looking at doing a mitosis, and one of the big misconceptions with students is the uranium splits but then it creates the same nuclei that it was before. So it's just making sure that they're kind of key that isn't happening. So you've got your two new nuclei, and then also getting the idea that there are 3 neutrons also released. So obviously you could then have another tub and think about the extra neutron then creating a chain reaction with another uranium-235. And the other thing to think about is one of the things which is quite frequently missed from students in exam questions is thinking that it's not just that that's released, but it's also, hopefully you can see my little wave type from the excess mass which is coming out, so representing that the excess mass is actually energy. So linking in with kind of what they'll be learning about at A level, so thinking that you've got your mass energy is conserved, so the amount of mass before and the mass energy after are going to be equal, and that excess mass is then turned into energy, which is why we do induced fusion in terms of power stations, to make sure that we release that energy, as students quite often remember the chain reaction, but sometimes they forget that part of that is it's releasing energy, which is what we're after. That's one of kind of the benefits of looking at this model. You can also have a look at using Lego, and that's quite useful because you can think about the number of protons and neutrons before and the number of protons and neutrons after. However, one of the issues with that can be it can kind of confuse students when we then think about beta decay, because they can think that you always conserve the number of protons and neutrons before and after the interaction, which isn't the case in beta decay. And obviously you can then demonstrate that you have this excess energy which is released.